Yes, acidity of phenol. This is a phenol, and this phenol is mixed with water and it dissociates and forming here phenoxide ion and the proton. Now the important part is the acidity of the phenol can be explained on the stability of okay, let me write this. The acidity of phenol phenol can be dependent on stability of phenoxide ion. So this is what we have, phenoxide ion. So how the phenoxide ion is stabilized? There are two possibilities are there by that the phenoxide ion can be stabilized. One method by resonance. The second, we can stabilize the phenoxide ion by placing the electron withdrawing group on benzene ring. Okay, so now overall we'll see one by one. The first one I'm going to write here. The first one is the resonance stabilization of phenoxide ion. Okay, let's move for the structures. First I will write here phenoxide ion having here O minus. Now this negative charge delocalize here, as this carbon already having 4 bonds, right? Here 3 sigma bond and pi bond is there, and new pi bond is forming, and therefore this pi bond can migrate to the next carbon, and by that what happens, the resonance structures are formed here, and that we have to write in the square bracket. So here the benzene, and here let me write here double bond O. Now there is no negative charge on the oxygen. Whatever the negative charge is there, it is flowed and moved to this carbon. These 2 bonds we have to keep as it is. Don't disturb them right now. Now you have to disturb the next pi bond, because this pi bond get migrate here, and by this charge become n bond and this bond becomes charge, and we get another resonance structure. This is negative charge, here double bond, this is as it is, no, don't alter it right now. Now it is double bond O. Again here new resonance structure is formed. Now this negative charge is delocalized here and forming a bond, and this bond is converted into negative charge. Okay, now we get another resonance structure. So here the new bond is formed, old bond, double bond with oxygen. This time the negative charge is here. Now at the end this negative charge become bond, and this pi bond becomes negative charge on the oxygen. Here the resonance ends, and the final structure is like this. Where the double bonds are just shifted here. If you check here, double bonds, they are shifted compared to here, and now we have O minus here. Okay, in this you can notice that these are the some structures where oxygen do not contain any negative charge. In these structures oxygen do not have negative charge. negative charge. So this suggests us something very interesting. It suggests us that phenoxide ion is stabilized. Phenoxide ion get stabilized due to resonance. Due to resonance. This is the explanation we can provide for the resonance stabilization of the phenoxide ion. Okay. If there is another method is there, that is the second one. We can write a second one, that is placing electron withdrawing group on benzene ring. This is also one method is there, and by that we can stabilize the phenoxide ion. Now here is phenoxide ion, okay, and here is O minus. Okay, now there is some group is attached here. Okay, group Z is electron withdrawing group. This Z may present at ortho position, para position, or at the meta position. Okay, you should remember that ortho and para positions are there. You can say that the effect is more effect will be there. Okay, and para have least effect. Okay, so therefore we can say that, so here the stability increases. Okay, almost you can see that ortho and para positions shows the same kind of resonance. Ortho and para shows same amount of resonance. So meta don't have it shows resonance, but it do not affect the negative charge present on the oxygen. So meta do not affect the negative charge on oxygen by resonance. So this is all about, students. Hope you understood this. Thank you for watching.